the colloquium of the department this year. This colloquium is also part of the joint initiative, the Joint Mathematics Colloquium between ICMAT, Universidad Complutense, Universidad Carlos III, and DAS. So our speaker today is Dan Král, who comes from Masaryk University in Brno. Dan defended his PhD in 2004 in Charles University in Prague, and he has held positions in the Technical University of Berlin, at Charles, at Georgia Tech in the US, at West Bohemia, some short stint at Warwick, and then finally he's a professor at Masaryk University at the Faculty of Informatics, actually. Dan's research is generally about discrete mathematics, particularly combinatorics and graph theory, but also their applications to computer science. Dan's production is quite impressive. He has published over 150 papers that I could see. He has supervised 9 PhD theses so far, plus 2 ongoing. And his work has received recognition. As a student, he won the International Olympiad, but he also got the European Prize in Combinatorics for solving the Plummer-Lovász conjecture in 2011. He also got another prize in mathematics and statistics, the Philip I cannot pronounce it, Leverhulme, in 2014. And in 2020, he was named a Fellow of the American Mathematical Society for his contributions to extremal combinatorics and graph theory, and also for his service to the profession. Among this service, there's one thing I want to highlight. He's an editor of a journal called Advances in Combinatorics, which is one of these overlay journals, archive overlay journals, which has the Diamond open access system, which means that there are no fees either for authors nor for readers, right? This model that was started with journal Discrete Analysis, I believe, and this journal Advances of Combinatorics is part of, it's a member of what is called the Free Journal Network, which is the network advocating for this kind of open access system, which, at least to me, I'm editorializing here, seems to me like the healthiest one available so far. So his title today is Analytic Approach to Extremal Combinatorics. Dan?
Thank you for the introduction. It's a great pleasure to be here. And I really appreciate the opportunity to introduce my research. And I will be talking about analytic approach to extremal combinatorics problem. And I have particularly decided to be highlighting my recent work, which concerns some Ramsey type questions. So I will start with a general introduction to Ramsey theory. And I think Ramsey theory in a certain way can be summarized in a single sentence, which says complete disorder is impossible. So essentially Ramsey type statements are about saying that if we are given large discrete objects usually, but not necessarily, we can find a substructure which is somewhat structured. And I'm sure everybody saw the simplest possible Ramsey type question, a Ramsey type result, which actually precedes Ramsey theorem, and that's a pigeonhole principle. So the pigeonhole principle says that if I have n balls, I color them with k colors. It's not possible that whatever balls I pick, they will have different colors. I will always find some number of balls that has the same color. And I just put here a small illustration. Of course, this is a trivial statement. And the first result, which is non-trivial and that started Ramsey theory, was a result due to Ramsey himself in 1930. And what he proved was that for every small n, where exists a capital N, such that if I two color pairs of endpoints, so I prepared here some examples. So we think of this as 5 points with pairs colored. So the color of the pair I depicted by drawing a line between the pair and assigning it either red or blue color. And Ramsey's theorem says that for any small n, if I take sufficiently many points, I will always find the set of a desired size such that all pairs are monochromatic. So let's say I'm shooting for a triple of points such that all pairs are monochromatic. So taking 5 points would not suffice, because if I color, so let's say I color all the pairs of 5 points as is depicted in this picture. So let's say this is 1, 2, 3, 4, 5. So these 5 pairs get blue color, these 5 pairs get red color. I will not find here 3 points that would have where 3 pairs would have the same color. However, in this picture I do. So for example, this triple of points, where all pairs are red. And or I can take also this triple of points and they also red. So Ramsey theory actually is not only about and I will call this object a graph, but before I define it, I want to say that Ramsey theory contains many further statements. For example, another classical result which belongs to Ramsey theory is the van der Waals theorem, which says that for every number of colors and every length k, if I take integers between 1 and n, where n depends on r and k, and I color them with r colors, I will always find a k-element arithmetic progression. I prepared an example. So let's say my integers go from 1 to 11. I color them red and blue like this, and I can find, I hope the bold font is visible, I can find a blue arithmetic progression of rank 4. So van der Waals theorem, which is another classical result from this area, says that for every number of colors and every length, where x is an n, that if I color integers between 1 and n with the given number of colors, I will find a long arithmetic progression. And this theorem is actually implied by something which is called the density version of the statement, which is the famous theorem due to Masaryk, which actually says that instead of having coloring, which in principle brings some structure, it's enough to have a dense subset of integers. So Masaryk theorem from 75 says that for any density and any length we wish, if we take a subset of sufficiently many integers that has enough elements, so basically the number of integers I need to take depends on the density. So if I want a sparse subset, of course I will need to take a very large n. I will find a k-element arithmetic progression. So this is of course a generalization of Rod's theorem from the 50s, which said the same statement about 3-element arithmetic progressions. That I prepared here again a small example. So let's say this is my subset of integers, and the 3-element arithmetic progression that I can see here is 3, 6, and 9. There have been many various extensions. For example, Hell's-Jewett theorem about combinatorial lines, and there's also a whole body about infinite Ramsey type statements. But at this talk, I actually want to focus on a question that stems from the original Ramsey theorem. Maybe I should have mentioned at the beginning of the talk that if there are any questions, then of course feel free to interrupt at any point. I will be happy to stop and explain in more detail.
I actually have one. So Semitic theorem implies van der Waals
Correct.
theorem, but of course it's 50 years old, younger. So the first proof, how did it go, or what did it use, or?
So the van der Waals theorem can be proved purely combinatorially.
Okay.
Masaryk theorem, it's it's often said it's kind of a precursor of hypergraph regularity. So it's kind of based on some kind of let's say like entropy increase argument. So somehow like in particular, and I will briefly mention regularity later in the talk. I will only mention it for graphs, but there's an extension to hypergraphs, which graphs are subsets of pairs of vertices, hypergraphs are subset of k-tuples, and one can derive Masaryk theorem from the hypergraph regularity and its consequence called removal lemma, for example. So definitely the density version, as you correctly noticed, I should have said, but of course the density version implies a coloring version, because if I have a coloring with k colors, then necessarily one of the color classes has density at least 1 over k. But the density version is much harder to prove, And it's not actually the case that if one has a coloring version, there's always a density version. It always depends on the kind of the problem one is looking at, but it's the case for arithmetic progressions. Thank you. Thanks for the question. Good. So I was trying to avoid using the word graph, but I will not survive the whole talk. So I have to define it now. So graph is a combinatorial object which is particularly important in computer science because it models various kinds of networks. And a graph formally is a pair of two sets. One is set of vertices. So I prepared an example, but I'm slightly worried that A, B, C, D, and E are not really visible. So there's a set of vertices, and some of their pairs are distinguished, and these are said to be edges. So this is a visualization of the graph which have 5 vertices, and these are the edges. And I do apologize that this A, B, C, D, and E is perhaps not the most visible. So if I want to state now Ramsey theorem in the language of graph theory, I will be saying that for every n where x is a capital N, such that if I take a graph that has all edges, these graphs are called complete graphs. The complete graph on n vertices has n vertices and all n choose 2 pairs are edges. And if I color them with 2 colors, I will find a monochromatic copy of a small complete graph. So this is again an example that I cannot, there's a 2H coloring of K5, the complete graph on 5 vertices where I cannot find a monochromatic triangle. And these are different colorings of the complete graph on 6 vertices, and it can be checked that each of them contains a monochromatic triangle. And the quantity that I want to talk now a little about is what is the smallest n, smallest capital N for the small n. So what is the smallest size of the complete graph that guarantees to have a monochromatic complete subgraph of a given size. And this is called the Ramsey number. So this example shows that the Ramsey number for free, if I want to have a triple of vertices such that all edges between have the same color, it's not enough to take K5 because in this 2H coloring of K5, I will not be able to find a monochromatic K3, but it can be actually shown that the R3, that the Ramsey number for free is equal to 6. And it's a simple argument which one can very easily teach in one of the first lectures in the freshman course as an example actually of a proof. So this looks like the things should be easy. So clearly R2 is 2 because if I have 2 vertices I color the edge, I trivially find the monochromatic edge. R3 is 6, R4 is 18. So it looks like things should be very easy. Unfortunately, already computing R5 is incredibly difficult, and there is this famous quote of R' which says that if an alien land on Earth and they tell us that they will destroy us unless we tell them what is the value of R5, then we still have a chance to survive. So what we should do is we should gather all mathematicians, all of us, with all our colleagues from all the countries, work hard with all the computers, we will compute R5. But if they ask for R6, we will have no chance. What we should do is we should fight. So the current bounds are these. So for R5, the range, as you may see, is rather small. For R6, is larger, and there hasn't been actually so much progress in the recent years. But I'm very happy that I can report that there has been a progress on the upper bound or R6. So maybe at the end we will even survive R6. And this is a very fresh result from this year due to Sergei Norin, Jeremy Turko, and Jan Volec, who's my former PhD student, one of those 9 that defended under my supervision. And as you see, they actually shortened the interval by 1/3 using so-called flag algebra method, which is closely related to graph limits and the analytic approach that I will be talking later about. So these are the small values. One can also ask, what about the asymptotic? What about the large values? So So how we can like prove some lower bound, and often in this area, if one wants to show a lower bound, one takes a random object. So in this case, what one would do, one takes a complete graph on capital N vertices and colors the edges randomly red and blue, and computes the probability that there is no small complete subgraph which is red or blue. And this actually gives a lower bound which has been unchallenged for, I believe, 70 years. And for the upper bound, one can do the inductive argument. There have been some small improvements, but until this year, the exponent stayed 4, and there has been a major breakthrough, actually earlier this year, due to Campos, Griffiths, Morris, and Saharas Goodhead, and they improved this bound by a little bit, but it's an amazing result because like there have been like many attempts for almost 70 years, and this breakthrough actually attracted a big attention in the community. Like for example, Gabers tweeted that he attended this marvelous seminar in Cambridge given by Julian about the improvement of this bound. So there have been also like a recent progress on the upper bound. So the question that I want to be looking at this talk is a related question, and it's a quantitative version. So what we know is that if I have a sufficiently large complete graph, I color its edges, I find a copy of the monochromatic small subgraph. If the graph is large, I definitely don't find a single copy. There must be more copies. And the question is how many? So if I am looking, for example, for triangles, monochromatic triangles, so this is my edge coloring, and I have one monochromatic blue triangle here, another monochromatic blue triangle here, another here. I try to draw them with bold edges. I maybe should have I also try to change the color, but I don't know how much it's visible. I guess like those sitting in the front may see it better. I was hoping it would be visible more. Nevertheless, I want to be looking at the quantitative question. I am guaranteed that there will be a triple of pairs such that all, triple of points, triple of vertices such that all pairs have the same color, and I am wondering how many such triples I can see. And in particular, is the random 2H coloring the best possible? Like if I'm asking, so of course if I would color all the pairs the same color, I will have a lot of triples. So the interesting question is what is the minimum number of triples, in general minimum number of n-tuples that I must always have. And I will not spoil the rest of the talk, I will just say that in case I'm interested in triples, the random coloring is the best possible. And this is a classical result due to Goodman from the late 50s. And it says that in any 2H coloring of the complete graph, the number of monochromatic triples is at least this number, which is the expected number plus some little order term, which is the expected number of monochromatic triples in the random coloring, because the probability a triple of points all pairs are red is 1/8, all pairs are blue is 1/8, so the number of monochromatic ones, the expected is quarter times. So I will say more about this problem, so this is the problem I want to study. I will approach it using analytic tools, but now I want to say a little bit about these analytic tools. So I will completely now switch the topic. So this is the question I will be talking in the last 10 to 15 minutes of my talk, but now I want to be talking about the methods, about the area which brought the right tools to approach this question. And that's an area of so-called graph limits, more generally combinatorial limits. And this area of combinatorics provides tools to represent and analyze large graphs using analytic objects. So it's originally started at Microsoft Research, where Borgs, Childs, and Lovaas started developing the theory primarily driven by the computer science motivations, but not surprisingly, the theory turned out to be very useful also to questions from pure mathematics, not only from computer science. So what is the desire? So I was talking about discrete objects. I was talking about graphs which had vertices and edges. And I would like to have an analytic object that would have the same key parameters that I can kind of work with and be able to say, based on some properties of this object, something about the discrete question I started with. And of course I want like some kind of robustness. Of course, like it's very easy to come up with some approximation, some visualization, but I want this object to actually somehow not only visualize the discrete setting, but also that if I'm looking at different parameters of it, these parameters must somehow interplay between each other, because this is what I will actually need to be able to say something about my original question. And also, like, I want these objects to kind of be attached to this discrete setting. But somehow, if I have some large, whatever this object will be, and I will say it in 2 slides, I kind of want these objects to be attached to the reality in the sense that if I have some large object that represents something, I can get also the discrete objects that are similar to it. So I call this assembly. And fortunately, in the case of graphs, but also in the case of some other objects like hypergraphs and permutations, we able to develop such objects. And actually, in the case of graphs, the theory is heavily building on the regularity lemma that I have mentioned earlier. So the regularity method, which was developed by Andreas Semeredi, and it was one of the key achievements in which was mentioned in the citation of his Abel Prize in 2012, says that if I have a large graph, I can decompose it into finitely many pieces, but these pieces will interact with each other in a quasi-random way. So I can approximate a large graph by a small number of parts that will have a controlled interaction. So I prepared here an example. So for example, this should illustrate that I can split the graph into 4 parts, such that the edges between these parts, so these parts will be huge, and the edges between these parts will be somehow almost randomly distributed. It will look almost like I threw them randomly in. I will not see a denser part or a sparser part with given densities. So I don't want to state the statement of the regularity lemma, but how one should think of it is that I am given a graph, I can split it into finitely many parts, and these parts with each other interact in a random looking way. And this is useful because it captures the local and global properties, so it's actually the essential brick for the robustness that I was mentioning on the previous slide, and had many applications, including in computer science so-called property testing algorithms, and also the generalization of to hypergraphs of this statement, which just I'm mentioning for graphs, yields that dense subsets of integers have arithmetic progressions of arbitrary large length. So I don't want to state the regularity lemma more precisely, but this is what is actually hidden behind the graph limits, which now I will say what they are. So, and I will demonstrate it on a single problem. I will demonstrate it on a classical statement from extremal combinatorics, which is Mantle's theorem. So let me first now say what are graph limits. If I lost you on the previous 2 very abstract slides, please try to reconnect. So I want to replace a large graph. So for example, I'm taking this graph, which has 2 sets of vertices with all edges between, and I'm thinking of kind of a sequence of graphs where the number of vertices is, let's say, 2n. I have n vertices on one part, n vertices in the other part, all edges between, and I'm thinking of this sequence for n growing to infinity. So one way to represent these graphs would be by the so-called adjacency matrix, which is a matrix with vertices and columns and rows indexed by the vertices, where I put a 0 if the vertices are not adjacent and 1 if they are adjacent. And actually this will be the matrix, if I apply the regularity lemma to this graph, it will be the matrix which will produce by putting the first part from the regularity partition as the first interval and the second part as the second. And if I kind of start thinking about how this matrix will look if n goes to infinity, it almost looks like a continuous function. It looks like a function from 0, 1 squared to 0, 1 with zeros in 2 quadrants and ones in the other 2 quadrants. So I'm putting the origin of the coordinate system in this corner just to have the analogy to the adjacency matrices. I know that statisticians that also use graph limits actually put it in the corner when one would expect it, but in this talk I want to have the analogy with the adjacency matrix. So graph limits for me will be so-called graphons, which are functions from the unit square to unit interval. So the parameters represent vertices, and the values that I'm getting represent the density of edges between vertices, and I can think of them as the limits of regularity partitions, and there's a lot of math kind of hidden behind the scenes. So in particular, if one wants to justify that this is the right object, one can use martingale convergence, or one can talk about exchangeable random arrays from probability theory. So I don't want to do any of this. I just want to sell to you that if I have a large graph, I can think of it as kind of the limit of adjacency matrices. This looks like kind of a kindergarten idea, but actually it works, and there's lots of theory which was developed by Borg, Chayes, Lovász, and their collaborators that actually links these analytic objects to discrete objects in the way we wish them to be linked. And I can talk in particular about the densities of different subgraphs. So for example, edge density, as you would expect, would be just the integral, because I'm thinking of the values as the densities between different small sets of my large object. And if I want to compute the density of triangles, the density of K3s, the density of triples of points that are all joined by edges, I will just compute this triple integral. And in this setting, the very classical Mantle's theorem from which is more than 100 years old, actually would be saying that if I forbid a triple, if the measure of triples of points x, y, z such that all these quantities are non-zero is actually 0, then the edge density must be at most 1/2. And this is a very classical result, which was of course proven well before the graph limits. It's not very difficult to prove, but this is the statement in the graph limit. So of course you may wonder, what is this good for? And I think one of the recent successes in extremal combinatorics was so-called Fleck algebra method of Rasborov, which is very closely linked to these analytic representations. It can be developed independently, but is very closely linked and made a progress on many problems that we couldn't solve for decades. However, I want to, before I go back to Ramsey theory, I want to talk a little bit about more generally what were our hopes that these methods can help us in extremal settings. So what is an extremal setting? Extremal setting is where I fix some densities. For example, I say I have no triangles and I'm asking maximize some other quantity related to some graphs. So this leads us to something which is called finitely forcible graphons. And a graphon is finitely forcible if I have a finite set of density constraints that this is the only graphon that satisfies, of course, up to measure-preserving transformation of vertices. So, for example, this graphon, which is the graphon we saw on the previous slide, is finitely forcible. And all these graphons that I have depicted here are finitely forcible. And they look very simple. Just like if one looks at them from the visual point of view, I mean, these graphons I should have mentioned actually correspond to so-called stochastic block models in probability and statistics. They look really simple. And for each of them, there's a finite set of graphs such that if I fix their densities, this will be the only graphon that satisfies this constraint. And it was somehow hoped that this.
Just one question. What's the grade?
So
I guess that white and black are 0, 1 and gray is.
And gray is between 0 and 1. So for example, this is constantly equal to 1/2. So there is. So if I take a sequence of graphs to which I throw edges randomly, I put an edge with probability, let's say 1/2, I will see no structure at all because I threw edges randomly. And this will be the graphon that represents such a sequence. So So the grays are different as represented in this regularity partition in the semi-radius sense. Like the edges between parts are distributed randomly, but it doesn't mean that I have all edges or no edges. I can have like half edges, 3/4 of edges, and the different shades of grays corresponds to the proportion of edges present between different parts. Yeah, I should have included one of these examples on the previous slide, but I already found it, but I put here quite a lot of figures. Thanks for the question. So Lovász conjectured that if I take an extremal graph theory problem, and by extremal graph theory problem, I actually mean a problem that maximizes some linear combination of subgraph densities, then it will always have a finitely forcible solution. And it was hoped that somehow this can be a new way of kind of approaching problems in extremal graph theory. That we will take an extremal graph theory problem, if it has a finitely forcible solution, and we can prove these finitely forcible graphons have simple structure, which if one looks at these examples, they look simple, then we can be able to actually say something. And in the next 5 minutes I tell you that this is unfortunately as false as possible, that both these arrows actually fell terribly. So let me start with the second arrow. So what does it mean to have a simple structure? So of course this needs to be mathematically quantified, and Lovász and Szegedi, they had several conjectures what a simple structure should mean. So they defined a topological space of so-called typical vertices, and one of their conjectures was that this space should always be compact. And that was actually our very first result in this area with Roman Glebov, a postdoc of mine, and Honza Volec, and we disproved this conjecture. I had another conjecture that the space should have a finite dimension. I kind of intentionally didn't say what exactly dimension they mean, but we basically, with Roman and Terka Klimoshova, another PhD student of mine, we showed that whatever dimension you wish to have, the answer is no. And then we constructed some other examples, but at some point, like we thought, okay, like this looks like a good machinery for producing papers, like, you know, we can, and this is maybe not what we should do. So with Jay Cooper and Taiza Martins, Jay was actually later a PhD student of mine, Taiza Martins was a PhD student of mine at the time when we worked on this problem. So we actually showed that finitely forcible graphons can contain arbitrarily complex subgraphons. So if somebody comes to me and gives me a graphon and tells me like, can I find this in some finitely forcible graphon, then the answer will be yes. And I prepared an illustration, but I'm not very good at illustrations, so I decided I will be doing a slide stealing. So I stole a slide from Lovász's Abel Prize lecture, and he gives an example, and I think it's a much nicer example than I would ever be able to come. So for example, if this is my graphon, so of course we need to align it to be symmetric. I can embed this graphon with, I need some arbitrary structure around, a kind of auxiliary structure to kind of glue it in, but I can embed it, and this graphon will be finitely forcible. So, for example, cat be finitely forcible. So basically this dismisses all the holes that the second arrow can be true. So there's no chance these finitely forcible objects can be simple. But still maybe the first arrow is true. So there is this, there was this conjecture that if I'm looking at a problem from extremal graph theory, I'm thinking of it as a linear combination of subgraph densities, there will be, I can maybe add some additional constraints, and it will finitely forcible. And as I said, it's not true, unfortunately, with Andrzej Kresik, who was a postdoc of mine, and notice this is Lovász Jr., not this Lovász, that we actually showed that there are extremal graph problems, that however many finitely constraints I add, there will not be a unique solution. And I prepared here an example, or actually our construction. So this is the graphon we constructed. I don't want to go too much into it. As you see, it has some structure. So actually what we did is we used our previous universal construction, this result with J. Cooper and Tyson Martins as a black box. And when we kind of started varying some parts of the graphon in a controlled way and using implicit function theorem, we showed that however finitely many constraints one can add, there will always be a part of this graphon that will not get completely fixed. So I'm not going to kind of talk more about it. Nevertheless, the story is this completely fat. So I believe I still have like 10 to 15 minutes. It's not a little bit late. So now I want to go back to the Ramsey theory and say that actually even if this line was failing, still graph limits are very useful, and they actually turn out to be very useful for the problem that I was present. So let me go back to that problem. So Ramsey's theorem again, and I am asking what is the minimum number of monochromatic copies of a small complete graph in some large complete graph. And R' actually in 62 conjectured that the random 2H coloring is the best possible. This H will be explained in a second, just ignore it for the time being, for any complete graph. So there was this Goodman's bound, which I mentioned, which was saying that the random coloring is the minimizer for the monochromatic copies of K3. R' conjectured that actually for K4, K5 it's also the minimizer. And a more general conjecture, okay, maybe let me now define the notion that I will want to talk about, and that's the notion of common graph. So in more general, I want to be talking about the minimum number of monochromatic copies, not necessarily of a complete graph, but maybe some other graph. So somebody comes to me, gives me a set of vertices and edges, and asks me, minimize the number of monochromatic copies of this graph in a 2H coloring. And if the random coloring is minimizing, then I will call this graph common. It sounds like a very strange name for this concept, but somehow it's meant that the graph is commonly appearing in the random H coloring. So in other words, this conjecture of R' says that complete graphs are common, and there was a more general conjecture due to Beer and Rosta that every graph is common. So basically these random 2H colorings, it was conjectured that this is always the minimum. And given how I'm saying it, you perhaps would guess that the answer is no. So this is the definition again. Maybe this might be a good time to actually formulate it in the graphon language. So the graph is common if the random 2H coloring minimizes the number of monochromatic copies. And if one wishes to formulate this problem in the language of graph limits, then I can think of red edges as a graphon. So basically, I remove blue edges, I just look what's left, and this will be one of my graphons. The other graphon, not surprisingly, will be 1 minus, because the complete graph is, I have all edges. And then I'm basically asking for an inequality of this type. Yeah, so this is the number of monochromatic copies in the red color, in the blue color, and this would be in the random coloring. So if for every graph on W this inequality holds, the graph H is common, meaning the random coloring is the minimizer. So these are the conjectures. I mentioned Goodman is common, and these are the bad news. So if I take a triangle with a single edge, so this is a 4-vertex graph which consists of the complete graph on 3 vertices plus an extra edge. This is not common. So this proves the Burr-Rosta conjecture. Thomasson, also in late 80s, showed that the only complete graph that's common is actually K3, and of course addition K2, which is common for trivial reasons. And more generally, he showed that as long as a graph contains K4, it's not common. So that looks like actually common graphs are very uncommon, right? But they're very rare. And that actually is a question like, are there some non-trivial common graphs? So one class of graphs which is believed to be common is the class of so-called bipartite graphs. So let me define them. So for that I need a concept of the chromatic number. So a chromatic number, and I prepared an example. So the chromatic number of a graph is the smallest k, such that I can partition the vertices into k sets, such that within each of these sets there is no edge. So this graph has chromatic number 2, where I can partition the vertices into red set and blue set. This graph doesn't have chromatic number 2 because I have these 3 mutually adjacent vertices. So I cannot put any 2 of them to the same set, so I need at least 3 sets. And 3 sets will do as it's drawn here. So one set will be red, one will be green, and one blue. And of course, for any complete graph, if I have n vertices with all edges between, I cannot put 2 of them to the same class because I want them to be edgeless. So I will always need n classes. And bipartite graphs are those that have chromatic number 2. And now I want to mention one of the most major problems in extremal combinatorics, which is Sidorenko's conjecture. And Sidorenko conjecture says that if H is a bipartite graph, so its vertices can be partitioned into 2 sets that edges go only between, when the density of that graph in any graphon is at least the edge density of a graphon powered to the number of edges of H. And if this is satisfied for every graphon, then of course H is common because one just applies convexity. And this statement looks like something that should be easy to prove, but it's actually proven, for example, for complete bipartite graphs, even cycles, but in general, it's widely open. And let me try to convince you it's a difficult problem, and I will not convince you by my quote, but let me quote Gavers from his blog, when he posted about the entropy method that was developed by Szegedy to attack this conjecture. And what he wrote was that this feels like a kind of statement that's either false or has a simple counterexample or a simple proof, but this impression is incorrect, and it's very incorrect. So there's even a 10-vertex graph which is bipartite for which we don't know whether the conjecture is true. However, the message of this slide is that maybe this chromatic number has to do something with being common, because Sidorenko's conjecture, which is widely believed to be true, says that all graphs which are bipartite, where chromatic number is 2, are common. And we have seen on the previous slide that if I take K4, which has chromatic number 4, then any graph that contains K4 is not common. So, and I want to say a little bit about the interplay of the chromatic number and being common, meaning the number of monochromatic copies minimized in the random 2H color. So again, K3 is common, so clearly 3 won't be the boundary. And it was open for a long time whether there are common graphs with large chromatic number, and until 10 years ago, large actually meant 4. So until like about 10 to 15 years ago, we didn't know a common graph with chromatic number 4 or larger. And the problem goes back to the work of Jagger, and Thomason from the 80s, and was repeated many times. For example, one can find it in the survey on extremal combinatorics and Ramsey time problems due to Konlon-Fox and Sudakov. So, as I indicated, we already knew the 4 chromatic common graphs. So this is a result from 2012 due to Hamed Hatami, Honza Hladky, my former PhD student Sergei Norin and Sasha Razborov, where we actually showed that the 5-wheel, a graph on 6 vertices obtained from the cycle of length 5 with adding a vertex adjacent to all vertices is common. We actually cannot show that all odd wheels are common until now. And the only proof that this graph is common is actually based on Fleck algebra, which is this computer-assisted method which is stemming from the graph limits. And this and last year, with Honza Volets and Fan Wei, she's now a postdoc at Princeton, we actually showed that there exist common graphs with arbitrary large chromatic number. And our approach is heavily based on graph limits, so we of course need to lower bound this quantity, and the way we do it is that we think of this W, this graphon, which is this function from 0, 1 squared to 0, 1, as an operator on L2, 1, and we analyze its spectra. So basically we think of it as an operator, analyze the spectrum. It sounds like a simple idea, but there's actually a lot of estimates. It's like 40 pages of quite heavy calculations. But of course we needed to come up also with graphs with large chromatic number that we believe are common, and this is what kind of closes this story in terms of the interplay of chromatic number. Of course, like it would be nice to have a classification, but there's not even a conjecture classification of common graphs. And I would maybe like to say one more thing about graph limits and actually canonicity. So, I forgot to mention one thing. So let me say that actually our techniques do extend to the notion of common with more colors, which you can imagine what it would be, that instead of coloring with 2 colors, I would color with K colors and ask whether the KH coloring minimizes the number of monochromatic copies. And what is actually interesting is when we observed with Honza Volec, Van Weijs, Sergei Norin, and John Noel, that a graph is K common for all K if and only if it satisfies Sidorenko's conjecture. So an alternative approach to Sidorenko's conjecture that I mentioned on the previous slide would be to show that every bipartite graph is K common for every K. So I want to mention a closely related problem, which is related to so-called locally common graphs. So in common, for common graphs, I am asking I'm asking about the minimum number of monochromatic copies where I don't put any restriction on the coloring. But what about if I'm just looking at coloring just somehow close to a random color? So this is a question that wouldn't make sense, or would be very hard to formulate in the classical setting. But it's not so hard to formulate in the graph limit setting. Because I can look at the 2 color classes, I can think of them as graphons, and I can just ask, are these graphons close to the 1/2 graphon? And I have different norms, different measures. So basically what I'm asking is, if I take U, which is a perturbation which is small, I will say in a second, slightly imprecisely what I mean by small, whether this inequality is satisfied. And if this inequality is satisfied, which is a local restriction of the common inequality, I will say that the graph is locally common. So this is not a notion due to me. This notion was introduced by Chouka, Hubai, and Lovas, and they consider 2 different notions. One is being common in a direction. So one fixes the perturbation, and then for that perturbation one wants a neighborhood which actually doesn't drop the number of colors. The other one is a stronger notion. One wants to have a universal bound on the perturbation. So this is the standard norm one is using in graph limits, so-called cut norm, and one doesn't want to drop for expression of this type.
The norm of H above is what?
So this should be the number of edges. So I should have said it. I do apologize. So this is the number of edges which I was using E of H most of the talk of. But somehow I was not consistent on this slide, and I usually follow distance notation, but I wanted this talk to be less notational heavy, so I started using E of H and was not careful with this one. Thank you. Yeah, so basically this is exactly the quantity that one would have in the random common. And they also provided some results which graphs are locally common. They show these 2 notions are different. And with Robert Hancock, who was a postdoc of my Matyáškans and Honza Volec, what we did, we actually for the directional notion, we actually analyzed the first 12 Taylor series and basically reprove all positive and negative results and prove many new results that appeared in the Chouka, Hubai, Lovas paper on this notion. So basically the point of this slide is to say that not only graph limits are useful to approach the problems, but also we now have the power to ask some kind of new types of questions. For example, we can be asking what happens if the coloring is actually close to the random coloring, which would be a type of question which would be hard to formulate using the classical tools from graph theory. So let me briefly summarize. So I talk about Ramsey theory. I try to convince you that complete disorder is impossible, both when one looks at graphs and so on. I talk about theory of combinatorial limits. It's an area which bridges various areas of mathematics. I mentioned statistics, There were lots of probability tools. It's using analytic tools to approach problem in combinatorics. It put new lights on many problems in computer science, being in property testing and some others. In particular, it provides great tools for asymptotic questions. Unfortunately, in case of optimal solutions, we saw that things are hard, but I think it's a good news because it means they're also fun to do. And when I talk about the Ramsey multiplicity, where I mentioned the applications of the analytic techniques, in particular the results we obtain by looking at graphons as Hilbert-Schmidt integral operators, and also that we can ask new types of questions that were not possible to ask before, that we can talk how some graphs are far from each other if we talk about the large graphs, and this of course implies also like we can talk about that colorings look or don't look randomly. And with this, I would like to thank you for your attention.
Questions?
You mentioned spectral techniques. Could you explain a little bit in a few words what is the relation with kind of questions?
Yeah, so this relates to this lower bound. So our graph actually is comprised of two parts. One part has high chromatic number, and that's a part we cannot say too much about. And then we have a part which has a lot of C4s, and C4s, like in the classical setting, they correspond to the trace of the fourth power of the adjacency matrix. And this also translates to the operator. So basically these C4s, the number of C4s that we would see is just the sum of the four powers of the eigenvalues. And our operators are nice because there's like compact, so we have the spectral theorem, so we can work with the four powers. And when we have these two parts of the graph, so which are connected by a path, and we need somehow like talk about rooted copies of this part and somehow translate it to the other, but walking along the path is nothing else than just applying this operator. And applying operator just naturally goes to the spectrum, right? Because I'm just looking at the decomposition of these rooted copies in the eigenfunction and look what the spectrum does to this. So essentially our proof has actually three regimes, but let me simplify it to two regimes. So one regime is that we're very close to the random coloring, and then basically we just say that the spectrum is more or less 1/2 and everything is around 0. Or our spectrum is very different, but when we get a huge boost in these fourth powers, that of course requires a proof, but it's possible to prove it if we very far from the random coloring, when the sum of the fourth powers is much larger, and even if we apply the operator to it several times to bring it to this high chromatic part of the graph, it doesn't decrease so much and it still gives us enough. So basically this is the I maybe became too technical, but essentially there are two ways how we link it. One is we can provide a very good lower bound on the number of copies of a part of the graph that contains a lot of C4s, because this essentially links to the fourth powers of the eigenvalues. And when the operator we also use kind of to walk along a path which connects the high chromatic part and the part which gives us the boost in the colorings and links them together.
Dario?
So my question is related to that of Dimitri and to what you were saying. So in the case of K colors, does your spectral analysis look like, or if you consider the case of K colors with your spectral techniques, look like the case of spectral analysis of weighted graphs? And so what relates that spectral analysis with clusters, and I'm thinking about the subgraphs as clusters or something like that. So,
okay, I'm not sure if I will answer the question, but we can talk maybe later because essentially like the third regime which I didn't mention. So I basically mentioned that we have this regime that basically the eigenvalues are very close to 1/2. So basically I have 1/2 and things very close to 0. Then I have this other regime that actually would mean that the first eigenvalue will be larger than 1/2, which of course gives me boost in the sum of the 4 powers. But I slightly, the third regime which I didn't mention and is also important is that I have a very sparse part in one of the colors. So basically in that part, if I try to root copies, I will be out of luck because maybe I even have a part that doesn't have any red edges. So I have a cluster of blue edges, and when or in case of K colors, of one of the K colors, and when I need to actually focus on this cluster and do something with it. So the proof actually goes that if there are no clusters, when I do my spectral things, if there's a cluster, I look at this cluster and try to apply induction based on K. If I do spectral things on it, if the remaining colors are distributed randomly, and if not, when I keep removing colors at the end, I end up with something which has all edges of the same color. So there's some clustering in the analysis too, but it's used just to, like, it's the third case that I kind of didn't mention.
Nice. And it's more related to the distribution of eigenvalues than to the support of the eigenvectors.
No, this actually, the problem would be with the support, because if somehow I have this part which misses one color, I will see it in the support. So basically these clustering techniques which actually appear a lot of in statistics that somehow, I wouldn't say we use them, but they somehow implicitly appear in the argument.
Thanks.
Can I ask, I don't know if it makes any sense. When you define the graph, you put this image, and you have this limit with this white, black, white, in the bipartite there, the one before. So you get that limit. But if I just relabel the vertices in an order, I will get a completely gray, no? If I get one up, one down, one up, one down.
That's a great question.
And
So
I can get basically any graph I want if I choose.
So the thing is that one cannot take a limit for an arbitrary permutation of the vertices, but one is taking a limit actually of these regularity partitions. So the regularity partitions, which I mentioned here, bring us some structure, and they would never partition the vertices in the way you mentioned. They would always put first the first part and then the second part. And for example, if I have something that looks in the limit like this, they would always put first these vertices, then these, then these, then these. Here they would put them in the increasing degrees.
This gray cannot come from a bipartite from which I choose.
Yeah, they come from like
okay.
bipartite graphs that I have no chance to reorder them to increase the structureness.
Okay.
Can you go back to the
This one?
No, I want to ask about this statement that being common is quite uncommon. Okay, so you found one 4-colorable graph, one graph with an example of a graph with chromatic number 4, which is not common. And then you found examples for all n's. I think you said that the one for chromatic number 4 was a wheel graph, but not, you don't know, or you didn't prove all wheel graphs are common.
Could you draw the wheel for me, because
Yeah,
I got lost there. What's the wheel? Sorry.
Cyclic with a
Okay, why does this have chromatic number 4? I'm struggling with this.
It has
I'm struggling.
it has an odd number, the cycle has 3, you need a 4.
Thank you. Okay, now continue. Sorry.
So my question is there, so how, is there necessarily one example for each,
so let me,
density? If I, let's say I let the number of vertices grow, then the proportion of common graphs, probably it's unknown, but maybe your idea, proportion of common graphs among those with chromatic number C and M vertices goes to 0, it's bounded below by 0.001 or?
yeah, so the proportion of common graphs would go to 0, and the reason is exactly this result that once I have K4, then I am no common. And so this immediately holds for all graphs, but it also translates to when one restricts the chromatic number. Because if I take a random graph, by random I mean I took...
Yes, you will have a K4.
I would have a K4.
Okay.
But our construction is actually, and I didn't want to formulate a theorem, but our construction is actually not that we constructed one graph, but we actually showed that one can take a graph if one takes a graph, and we proved in the paper graph 32, but actually we believe this graph assumption can be brought down all the way to 4, and this I can find as an induced subgraph of a common graph. And whereas this classical result of R dash, where are high chromatic graphs without short cycles. So basically, this will be the part which pushes the chromatic number, and that's the part that we actually connect to this part, which on the other hand increases the monochromatic copies, which has a lot of C4s. So our result is that any graph with graph at least 32 can be found as an induced subgraph of a common graph. But we believe that this 32 can be brought down to 4, which would correspond to the results in the local Sidorenko setting due to Fanway and Jacob Fox. But we were not motivated to do it because we already had like 40 pages of actually heavy calculations, and this would mean maybe 60 or 70 at the end. So, and we thought that it's simply not worth the effort because we didn't see any immediate application for bringing this assumption on short cycles down to 4, which we believe is the optimum.
More questions? Well, if not, we thank Dan again. Andra.